Hello. In the last video, we derived the probability distribution for the canonical ensemble and the canonical partition function. We discussed how in this ensemble the volume and number of atoms are held fixed, but that the internal energy is allowed to fluctuate. The system is thus allowed to exchange heat with its surroundings, but is not allowed to exchange work or matter. The final results that we arrived at were as follows. The probability of being in any given microstate was given by the expression shown at the top of this slide, and the canonical partition function that is given by the expression shown at the bottom of this slide. Furthermore, we showed that the Lagrange multiplier that enters these expressions, beta, is simply equal to 1 divided by Boltzmann's constant multiplied by the temperature. We now need to do something with this ensemble. So with this in mind, our aims in this video will be to see how we can calculate ensemble averages and to introduce the notion of fluctuations. Before we go on to that though, allow me a short digression to show you a rather nice result. When we first derived the generalized partition function, we said that the entropy was equal to minus the information contained in the distribution. We then used this fact to show that the entropy for the generalized partition function could be calculated using the expression shown here. If we replace the sum over bk in this expression with the ensemble average of the energy, which remember is the quantity that we have not constrained to have a fixed value in the canonical ensemble, we get to the following expression. Rearranging this expression, we can then get to the following. We now recall that phi in this expression is related to the canonical partition function by the equation shown here. In addition, E minus Ts is the definition of the Helmholtz free energy, F, that we introduced when discussing thermodynamic potentials in the context of classical thermodynamics. We thus arrive at the following rather pleasing interpretation for the definition of the Helmholtz free energy. The Helmholtz free energy is simply minus kBt multiplied by the logarithm of the canonical partition function. In other words, our thermodynamic potential is connected to minus the logarithm of a probability. Hence, noting that the free energy for a set of states is low is in some way equivalent to saying that there is a high probability that the system will occupy these states. Let's now move on to the notion of an ensemble average. Let's suppose we want to calculate the average value for some observable A. Let's further say we know how to calculate the observable from the positions and momenta of the atoms in the system. We can thus write the ensemble average for this quantity, A in angle brackets, as the following summation. In this summation, Pj is the probability of being in microstate J. We know that for the canonical ensemble, this is given by the expression shown here. We can thus insert this into our equation for the ensemble average for the observable A and get the following. To be totally clear on this process of calculating an ensemble average, let's see how this would be done if we wanted to calculate the ensemble average of the energy. The function that calculates the energy from the positions and momenta of the atoms in the system is the Hamiltonian H. We thus have the following expression for the ensemble average of the energy. Looking at this expression for a moment, we might note that the right-hand side is just a derivative of the canonical partition function. Can you work out what we might differentiate the canonical partition function with respect to get this result? Pause the video for a moment and see if you can suss it out. I will tell you what we do on the next slide. We are coming back to the derivative, I promise, but we are going to take a circuitous route to it that starts from the following rather obvious equation. E to the minus psi times e to the plus psi equals 1. Now e to the plus psi is just the canonical partition function. So we can replace this term as shown here. We will then bring the e to the minus psi inside the summation and combine the two exponentials as shown here. Let's now differentiate both sides of this equation with respect to beta. It is easy enough to show that this gives the following. As always, take a moment to pause the video and work through this bit of differentiation yourself if you need to. In doing so, notice the minus sign in front of the summation. We can rearrange the derivative we just arrived at as shown here. In doing this, we have split the equation into two summations and noted that the partial derivative in the first summation does not depend on j, and that this can thus be taken out of the summation. We have also rewritten the exponential as a product of exponentials and recognized that e to the minus psi is equal to 1 over e to the plus psi. Look now at the quotient in the first summation. This is just the probability of being in microstate J. Furthermore, the summation runs over all possible microstates. This summation is thus simply equal to 1. The quotient in the second term is also equal to the probability of being in microstate J. Furthermore, this is multiplied by the energy for microstate J, and a summation is performed over all possible microstates. This summation is thus just the value of the ensemble average of the energy. We thus arrive at the following result. The ensemble average for the internal energy can be calculated by taking minus the derivative of psi, the logarithm of the partition function, with respect to beta. This is a nice result, but we can get to something even nicer and even more physically profound by taking these ideas a little further. In doing this, we start from the result that we arrived at when we took the first derivative of 1 equals e to the minus psi times e to the plus psi with respect to beta. We now differentiate this again with respect to beta and get to the following result. Once again, pause the video and take a moment to convince yourself that this is the correct result. We now note that in the last slide we found that the first derivative of psi with respect to beta was equal to minus the ensemble average for the energy. We can thus replace the first derivative in this expression with a minus the ensemble average as shown here. Next, we split up the summations just as we did in the previous video. Once again, we find that the quotient in these two terms is equal to the probability of being in microstate J for the canonical ensemble. We thus know that the second summation is equal to 1, and that the first term is the ensemble average for this quantity here. We can thus arrive at the following result that relates the second derivative of the logarithm of the partition function with this particular ensemble average. Now, if we have any familiarity with statistics, we recognize that the ensemble average we are calculating here is equal to the second central moment of the distribution. This is also known as the variance. In addition, because the term being averaged inside the angle brackets is squared, and because our energy will never be an imaginary or complex number, this variance or fluctuation will always be positive. The two results that we arrived at are shown at the top of this slide. We can combine these two results and thus write the second derivative of psi with respect to beta is equal to minus the derivative of the ensemble average of the energy with respect to beta. This is interesting, but what would be more interesting would be if we could calculate the first derivative of the energy with respect to the temperature. We can do this, however, by using the chain rule as shown here. Furthermore, we know that beta is simply 1 over kBt, and hence that the derivative of beta with respect to t is just minus 1 over kBt squared. We can thus connect everything on this slide and write that the fluctuations in the internal energy, shown on the left-hand side of the equation shown here, is equal to kBt squared multiplied by the first derivative of the internal energy with respect to the temperature. We now recall that the derivative of the internal energy with respect to temperature is just the definition of the heat capacity. We have thus shown that the heat capacity can be calculated from the fluctuations in the internal energy. We know that these fluctuations, the variance, must be positive as we are taking the average of a squared real number. Hence, we have shown once again that the heat capacity must be positive. This time, however, we have done so by considering the statistical properties of the canonical ensemble. To summarize then, we have derived the following three results for the canonical ensemble. We have shown that the Helmholtz free energy for the thermodynamic state can be calculated from the canonical partition function. Furthermore, we have shown that the ensemble average of the internal energy can be found by taking minus the first derivative of the logarithm partition function with respect to beta. Lastly, we have shown that the heat capacity can be calculated from the average fluctuations in the internal energy, and have thus demonstrated once more that this quantity must be positive. Thank you for your attention.